So Chapter 3, Descriptive Statistics. So you learned these last semester, but we're just going to give a really quick recap of some of the main highlights. So the sample mean is the average of the sample. We denote it by X with a bar over it or Y with a bar over it, and I typically call it X bar or Y bar. And the way you calculate it is to add up the observations in your sample and then divide by the number of observations. And we're going to think about the mean as the balancing point in a distribution. So if you think about the histogram of a data set, fill it with solid material and put a fulcrum under it, the mean would be where that fulcrum would go to balance the histogram, to balance the distribution. The median is the 50th percentile of the sample. Usually we denote that with a capital M. It's the middle observation in the ordered list if n is odd, and it's the average of the two middle observations if n is even. And we're going to think about the median as the equal areas point. It doesn't care about whether the distribution is balanced. It just cares that half the observations are above it and half the observations are below. All right, so consider the two following data sets. Find the mean and the median for both. This first one is 1, 2, 3, 4, 5. So let's find the mean. It's 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. So the observations add up to 15, and then we divide by the number of observations, which is 5. 15 divided by 5 is 3. Now the median is 3, because that's the middle observation in the 5 ordered values. So the median is 3, and the mean is also 3. In the second data set, what's the mean? 20 plus 4 is 24, plus 3 is 27, plus 2 is 29, plus 1 is 30. 30 divided by 5 is 6. Now the median is still 3 because that's the middle observation. So the median did not change and the mean went up to 6. So what happened here and why? Well, the mean was pulled up by the large observation, which was 20 in the second data set. In general, the mean is going to be pulled in the direction of extreme observations, and the median is not as affected. So if you have a skew or outliers, the mean is going to go in the direction of those outliers or the skew. So if your data is skewed right, then your mean is going to be greater than your median, because the skew in the right direction means you have extreme observations in the high end of the distribution, so the mean is going to be pulled up. If your data is skewed left, you've got extreme observations in the low end of the distribution, and the mean is going to be less than the median. And if the data is symmetric, the mean is going to be approximately equal to the median. If it's exactly symmetric, it'll be exactly equal. But typically in the real world, we have not exactly symmetric data sets. We have approximately symmetric data sets. All right, so when you have a symmetric data set, you're going to report the mean and standard deviation. But if you have skewed data sets, you're going to report the median and quartiles, maybe in the 5-number summary. Think about when you hear about home prices in the news. Listen carefully next time and you'll hear them mention median home price. The reason that they talk about median home prices is because home prices are skewed. They're skewed right. Mostly everybody lives in what I call regular houses, and then you've got always those couple neighborhoods that have really high-end homes in them, or even a few mansions here and there. So when you have skewed data sets, report the median and the quartiles. All right, the mode is another numerical summary. It can also work for qualitative data sets, for categorical data. So the mode is the most frequently occurring value in a data set. So the thing that makes it unique is that it does work for quantitative or qualitative data. And then finding the mode for continuous data can be tricky and is often not used. And as such, we won't talk about it too much this semester. We'll be using the mean most often and sometimes referring to the median. All right, so measures of variability. Our friend, the sample variance. We denote that by S squared. And that's the sum of the deviations of each observation from the sample mean squared, and then divided by n minus 1. And to put our observations, to put this numerical measure back on the scale of the original data, we take a square root of it to report the standard deviation. So the standard deviation is denoted by little s. We will not be hand computing it this semester. Hopefully you understand the properties of it from your previous stats course. We'll be using R to compute our standard deviation if we need it. The range is defined by going from the maximum observation in a data set to the minimum. So it's the max observation minus the minimum observation. And then the IQR, or interquartile range, is the distance from the third quartile to the first quartile. So Q3 minus Q1. An efficient way to communicate the measure of center and variation all at once is to report the 5-number summary. The 5-number summary is the minimum and maximum observations and the 3 quartiles. Remember that Q2, the second quartile, is the median. Q1 is the first quartile. It has 1/4 of the observations below it. Q3 is the third quartile. It has 3/4 of the observations below it. Similarly, Q2 has 2/4 of the observations below it, otherwise known as half or 50%, so that's the median. The coefficient of variation is the standard deviation expressed as a percent of the mean. So it is the standard deviation divided by the sample mean times 100. So think about a data set that has a standard deviation of 5 with a mean of 10. And then think about a distribution that has a standard deviation of 5 with a mean of 1,000,000. That means something different, right? So the coefficient of variation is a way that you can express that standard deviation relative to the sample mean. So it allows you to compare variation in data sets with different units or means. Chebyshev's inequality is one way that we can estimate the percent of observations that lie within a certain number of standard deviations of the mean. So it says for any population with a mean mu and a standard deviation sigma, the percent of observations that lie within k standard deviations of the mean is at least 1 minus 1/k² times 100. For example, what percent of observations lie within 2 standard deviations of the mean? Well, first of all, we have to figure out what k is. K is the number of standard deviations, so k here is 2. So we plug that into our formula and we get 1 minus 1/2². We plug 2 in for k in that denominator. And that's 1/1/4. 1/2² is 1/4. And that's 0.75 or 3/4. So at least 75% of observations will lie within 2 standard deviations. So that's a little application of Chebyshev's. And of course, it's for k greater than 1 because it breaks down for k equal to 1 because that's 1 minus 1, which is 0. So k has to be bigger than 1 to apply that. Now the empirical rule is a special rule for a way we can calculate the percent of observations that lie within a certain number of standard deviations, but it works for unimodal distributions that are fairly symmetric. We're going to see when we get to the normal distribution that it comes from the normal distribution. But for now, we'll just memorize it again. It says 68% of observations are within 1 standard deviation of the mean, 95% within 2, and 99.7% are within 3 standard deviations of the mean. So that means almost none, 0.3% of observations are going to be outside 3 standard deviations of the mean in a unimodal, fairly symmetric distribution. All right, a z-score is a way that you can standardize your data. So if you take an observation minus the mean mu divided by the standard deviation sigma, you're calculating a z-score. A z-score represents the number of standard deviations an observation is above or below the mean. Beware of using z-scores from skewed distributions. The z-scores end up having the same shape distribution as the original observations. So it's not appropriate to compare a z-score from a skewed distribution to a z-score from a symmetric distribution. So let's look at an example of this. Consider this housing data on the square footage for 100,000 home sales in Saratoga, New York. The average size of these homes is 1,755 square feet with a standard deviation of 620 square feet. Seeing a home 3 standard deviations above average is possible. That's the mean, 1,755, plus 3 times the standard deviation of 620. That would be a home size of 3,615 square feet. But being that extreme in the other direction is not even possible. So we take the mean minus 3 of those standard deviations and we get negative 105 square feet, which obviously doesn't make sense. Also notice that the z-scores will have the same shape distribution as the original observation. So what I've done here is I've taken, so this histogram is of the square footage of all the 100,000 square footages. But this one is me computing the z-score for each of those 100,000 observations and graphing that. The z-score from a right-skewed distribution will not be comparable to a z-score from a left-skewed distribution. All right, skewness and kurtosis are the last two topics here. Skewness has that kind of ugly-looking formula there, but what we want you to know is that it's a way that you can actually quantify how skewed a distribution is. Skewness is going to be less than 0 for skewed left distributions. It's going to be equal to 0 for that symmetric distribution in the middle there, and it's going to be greater than 0 for a right skewed distribution. Sometimes you'll hear skewed distributions described as negatively and positively skewed. That's where it comes from these skewness measures. And then kurtosis is another measure about the shape of a distribution. A very ugly looking formula. We won't ever hand compute it. But what I want you to know is that kurtosis equals 0 in the center distribution there. As it gets less peaked in the middle and has more in the tails, so it gets kind of shorter and wider, the kurtosis is negative. And on the right side, the picture shows a positive kurtosis, and that's when it gets skinnier and taller.